because my mic is muted. That's pretty funny. Yeah. So thank you for letting me know that my mic was muted, because all my levels were right, but no sound. But so I'm going to go through that little spill again about who I am. This is your first time on stream. My name's Jason Watts, CEO, founder of a little company out of the southern United States, Sweet Home, Alabama. I'm here in our lab in West Midtown Atlanta, just north of Georgia Tech. But if you don't know me, I've got about 24 years of experience now working with Siemens drives and PLC technologies. Been in the industry since I was about 14 doing stuff. So this channel is mainly about automation, mainly about technology, but today we are going to be kind of talking about just whatever that kind of comes up. And yeah, I've got to figure out how to get this on the right volume. There we go. All right, because today we're going through a couple of different things that in our Discord channel kind of been talking about. I put out a little at everyone in the off topic section just to see what anybody wanted to talk about, and I got a couple of responses back. Wanted to talk about the new S7 1200 G2, so the version 2 of the S7 1200. So we're going to be talking about that. We're going to be talking specifically about motion control, because the G2 is kind of targeted for this kind of trying to expand the motion control market for Siemens. This channel is really built around Siemens drives and Siemens motion technology. If you haven't checked out the rest of the channel, this is your first time here, hey, thank you for coming. Maybe you might want to look around and subscribe. But if you're on the stream now, go ahead and hit the like button to try to get the algorithm working on this middle of the day, Wednesday afternoon, day before a holiday here in the US. Just boring, regular Wednesday everywhere else in the the world. But yeah, if you're new to the channel, there's definitely a lot of stuff about motion control technology here, about Siemens mainly, but we also do a lot of other PLC topics as well, and some other things like production or custom mechanical design. And I'm going to go ahead and apologize for all the noise, because this is a warehouse, and that's really loud to me. Hopefully it's not too loud for you. But yeah, so on this channel, a lot of topics about motion control, different technologies that are PLC automation, because I've been doing industrial automation for nonstop ever since about 2014 now. I had a little bit of a break there that I wasn't in the automation world. I was in hardware design, but yeah, we're going to be talking about some cool stuff today. I talked about our Discord channel. If you have not signed up for our Discord channel, we are over 100 members now in the Discord, and that is the best way if you're going to want any sort of topic about like if you have questions about something that you're working through. We have a help desk in there. If you're designing some system and you have questions, that's kind of the best way. And it's a lot more than just me in there. We've got some really great members of the Discord that are also members of the channel that, yeah, they really help out. And it's really encouraging to see everybody help each other out in there. All right. Yeah, I'm glad you can hear my voice clearly, because, I mean, again, this is a shared warehouse space, so there's a lot of work going on here. I think it sounds like somebody's cutting some, I don't know. I'm going to think they're making some sort of like bespoke table for someone's high-end house over here in Buckhead. But it's probably a bookshelf. But anyway, we're going to be talking about the new motion control technologies available in the S7 1200 G2. If you are not familiar with kind of the Siemens way of motion that has kind of been moving away. We're going to talk a little bit about some of the options that you have in TIA Portal. Right now, there's really, for just general motion control, there's kind of there's kind of really two main options for kind of what we will call synchronized motion. If you haven't checked out, if you're not familiar with what I mean by motion control, it might be good for you to go through and check out the Motion 101 class that I did a few months ago. I've got a link in the description, and that class goes through pretty in depth about what on this channel I'll talk about motion control. Some people consider anything that has a motor motion control. Some people consider only motion control things that have like robotic synchronized axes, kinematics, things like that. Our definition here is really anything that requires position control for the most part. There are things that you might just not, that don't need position control, but in general, all the functions that we're going to be talking about require position control. And in order to get position control, normally you need to use an encoder. So that's kind of the general, my general method of kind of breaking down what motion control is if you're having to use an encoder for something, then it's probably motion control. And in general, we have had two different options for this type of motion control in the what's called factory automation world in the Siemens. And one is with technology CPUs, and then you have a platform called Siemens. And Siemens is very powerful, and it can do a lot. And this is what you normally will see on things like printing presses, and because it has its own dedicated hardware for these motion control kind of functions. It is its own beast. It has its own kind of programming language that it uses. Yes, you can do it in ladder if you don't really like yourself. But the best way to do Siemens would be with a programming language called ST, or simple projects can be done with a language called MCC, Motion Control Charts. But that's available in a package called Scout, and it's kind of its own programming environment. While it is in TIA Portal, it's kind of like hodgepodge together. It's kind of like a package inside of a package. Whereas with TIA Portal, the big advantage of TIA Portal is that it's all one database, it's all one project. You're working with HMIs, drives, PLCs, networking components, like all of that is in one project, and it's one database and one thing. Siemens kind of throws a little bit of a wrench in that because it's kind of packaged into it a little bit differently. The stuff we're going to be talking about is available on, or has been traditionally available on TCPUs. And what I'm going to do, and I realize I may not have had this pulled up correctly. Give me a second. I'm going to get this set up. Let's see, Sketchpad. So this is what we will be talking about later, this guy right here. But what I want to talk about right now is, let me get my browser window pulled up. That is not what I'm wanting. I forgot to set this up earlier, and it is not liking it. So give me a second and I'll try to get this. Well, maybe we won't. Maybe because I was going to show you on here the current line of technologies CPUs, and I'll do that. I'm just going to have to I'll just have to make something real quick on OBS Studio while I'm doing it. Thank you for your patience on this. I forgot to set this up. I was running a little behind. One thing about kind of running your own, running a business is if customers are running, then they kind of need you to work on stuff. And so I was dealing with a kind of a design issue this morning, and so it kind of pushed me later back into it. So let's go through and do this, and let's take window capture here, properties, and we're going to do this right here, and then we're going to make this visible, and there we go. All right, now I could actually talk about this, because this is kind of the technology CPU version. And one of the things about the 1200 and 1500 line is they introduced, it wasn't a full introduction, but they really expanded upon the concept of technology objects. And again, I have a lot of different videos on my channel that are based around these technology objects. So go through there. We're going to talk about some of those later, and we'll dig through that later. But what the technology CPU is a 1500 processor that has expanded motion control technology in it. And that's what the T is for. It's a technology CPU. And the way that they did this in the kind of new portal versions, so the 1200, 1500 versions, they used what a thing is called a motion control resources. And let me find where it shows it right here. So for this, you see you have these motion control resources here that are available to you. And each function will consume some of these motion control resources. And they're like, for a positioning axis, I think it's like 20 resources. And then for a speed axis, it's 20, a positioning, it's 40. And essentially what it's trying to do is tell you how much processing power you have available for these very specific functions. The TCPUs are specifically designed for it, and they have a lot of these motion control resources. The thing about it is you didn't have to have a TCPU to use these technology objects. You can use a standard CPU. And if we bring this up, we see that there are motion control resources available in these standard CPUs as well. And so what's funny is that technology CPU, that 1511T, looked like it had less resources. Yeah, it does. Siemens, why do you do that? That doesn't even make sense. So one of the things is that you can have your standard CPUs. Your standard CPUs have these motion control resources, but they do not have specific functions available to them that you might want. So a standard CPU was restricted to standard gearing. So you can do positioning, so you can do speed axes, you can do positioning axes, and you can do what is called relative gearing. So that means that the positions will be synchronized, but you can't determine where those are actually synchronized. Now, again, I go into deep detail in that motion control 101 class, and in the link below. So after this, feel free to watch that if you have more questions about what I'm talking about, absolute gearing versus relative gearing. Well, in order to do some of the more advanced functions like absolute gearing, kinematics, camming, those sorts of synchronized motions, you needed this TCPU. Well, one of the things that you have is we're looking at the 1500, and the 1500 processor is the advanced controller. And so when you actually, there is a lower end processor called the S7-1200. And we're going to be looking at what is available right now. And you'll notice, I don't know if it'll show on here, there actually is motion control resources available in the 1200 processor, but it is restricted to speed axes only. And so you can absolutely control motion, control a drive with the current series 1200s. I've got one back there on my shelf behind my 3D printer filament box that's blocking it. But on that 1200, you can absolutely control that little demo drive right there. You can control that with that 1200 using a technology object, but you can't do synchronized motion, anything like that. Well, apparently they did that to try and like delineate the different markets. They want to kind of say, hey, we have this lower end processor for these different markets, and then we have this higher end market or higher end processor that's a little bit more expensive that is still that kind of expands the technology. If you're doing these higher end motion, then you're probably going to be in an environment to where you can afford a little bit more. Well, that doesn't always quite work. And then you have competitors that are starting to kind of introduce these functions into these lower end processors. And so in response to kind of the current market, Siemens came out with the S7-1200 G2. And they announced this at Hanover Fair this year in April, and everybody is kind of going crazy about it because it is a 1200 processor that has built-in technology functions like a TCPU. So we're going to go through kind of like what this S7-1200 G2 has. And I want to say that the delivery for these is starting to become available. Like you can actually order them and you can get a delivery date. There are some other YouTubers that have gotten them, but I will say every G2 1200 processor I have seen on YouTube has been in the hand of a German-speaking YouTuber, and I think there's a conspiracy. It's almost like they have extra special access to it somehow. But anyway, there are some videos out there. There's Michael Gromless, I think, has, and I butchered his name, I know, but he has one. And I want to say that PLC Skill Tree has a video on them as well. And both of those guys do excellent content. And yeah, you can kind of see videos about those G2 processors. But let's go through these technical slides, which, by the way, link to these technical slides is in the description. And I'm going to go ahead and say, if you notice in the link on that, that's not a Siemens website, but this is a unrestricted Siemens slides, and we're going to go through these if you notice on the bottom. So these are by Siemens. This was announced at the Hanover Fair, and they kind of go through and talk about the different kind of demand that I was talking about. No longer are only your high-end, really profitable, like really expensive processes going to this these like higher-end motion functions. And so kind of Siemens is trying to open up market share by opening up these not necessarily lower end, but accessing these kind of like I guess the less expensive capital expenditures in these different markets. So what they've done is they have redesigned the controller based on new technology, and both of these products are coming in TIA Portal V20. If you notice on all of my streams and later on when we're talking about the different motion control blocks and everything, you'll see that I'm using V17. Well, I'm going to be upgrading to V20 for this very reason, and it's a long time coming. I don't normally upgrade every version just because we do so many different projects. It kind of is hard to go through the process of keeping up with versioning everything, and so we're kind of looking at this process. If you notice that everything seems a little bit more compact, everything is kind of more tightened up on everything, and that is kind of one thing that I'm like, might be a little bit more difficult because you're having to work with smaller wire size, smaller wires on these things. But if you're breaking that out to terminal blocks, field terminal blocks anyway, it's probably not that big of a deal. You're going to be working with some 22 gauge wire or something like that here and going out to your terminal blocks, and yeah, kind of going from there. So a couple of the things that I found really interesting on this is there is NFC technology built into these things. So you may or may not know that the 1200 has a built-in web server that you can create your own kind of built-in HMIs that you could just hit with a web browser. But there's some security issues there, and you're having to use JavaScript and kind of all of that, and so it doesn't really necessarily tend itself to a lot of use. But this NFC, you can actually come up and use NFC to pull data straight from the processor if you were right there at the processor, which I think is really interesting. And so that's really talking about TIA Portal. And here's what I was talking about. So the scalability, because of the hardware space reduction, if you were replacing a 1200 system with a 1200 G2, you know you're going to have enough space, and you're probably going to have an expanded space on it. It has the F versions, which there is a 1200 F version. The 1200 G2 is it has the same thing. There is an F version, and it has expanded modules because there was a little bit of limited offering, because they didn't really want to cut into their other F-class processors, the safety rated processors. I don't know for sure, and if anybody in chat is kind of sitting here and knows the answer to this question, but the S7 1200 could not do remote safety, so it didn't have the safety I/O, or at least at launch, it couldn't do like Profi safe communication to safety I/O. But I wonder if this G2 is, because that's a really big difference. Is if you have this little small safety processor and you can use your ET200 I/O, then yeah, that's a game changer. Either way about it, you have these new compact format safety modules that you can add on to it, and they're going to be at a lower cost point just because of the nature of the 1200 system. So we're going to go into a little bit of the technical details about some of the performance gains that it talks about on this screen here. And then we're also going to talk about the efficient motion control. And I want you to look at this word right here. Kinematics. I still don't quite understand how they can justify kinematics on a processor like this, but if you don't know what kinematics are, it is the higher end like robot control, like 6-axis stuff. And from a pricing and product portfolio thing, the fact that they're putting kinematics into a lower price point processor in their line is a very interesting choice. So I'm about to sneeze. Excuse me. But we'll move on. So kind of talking about all these different things. If you look at the new the 1200, the 1212C FC 14 and 14FC. So there's really technically only 2 versions of this G2 processor, the 12 and the 14. And then you have the safety version of each. And I will say that I think it goes into the next thing. It shows here that you have these technology objects, and there's a page here that actually goes through all these. It's kind of crazy at what you actually get. So here's the overview between the two, the 12 and 14. So you have this integrated I/O, 8 digital inputs on the low end, the 12, 2 Profinet Modbus TCP ports. If you're used to kind of using a Modbus TCP device and you're using Modbus, this is built in, ready to go for it. Communication modules, so that would be things like Profibus or external Ethernet IP or whatever that needs to be done on that way. I don't know if there's an Ethernet IP, but you can have these communications like an LTE communication card. You can have 3 of those, and then signal modules plus the communication modules, so it can expand on the low end up to 6 total modules, and on the 14, 10. And a signal board it's interesting that you could have 2 signal boards, because signal boards are actually hanging off the front of the device, which are interesting. Yeah, that's interesting. Actually, but so kind of just going through a bunch of the other stuff that we're talking about. Pretty basic stuff, form factor things like the terminal blocks that they're talking about. They're higher density and they're removable, so you just go in, pull them out, and you can wire them off of the device and then push them down in. And I want to say, is this the... Nope, this is the size. And I wanted to... So this is memory card. And so memory card, the little conversation about what is actually on the memory card versus what is the load functional memory on these things. Because if you notice up here, you're like, man, I only have 500K of RAM, 750K of RAM, 150K of program memory, 250K of program memory. That's not a lot. Yeah, you're right, but this processor shouldn't be doing a massive program. But the thing about the way Siemens PLCs operate, if you come from an Allen Bradley world, which, sorry I said that, the name on the channel, but if you come from an Allen Bradley world, you're not quite used to those really small numbers because of the way that Siemens handles tags. Just if you're from that background, in Rockwell, everything is 32 bits. So it's an actual tag. And so if you have a Boolean, which is an on-off, like a 0 or a 1, that's 32 bits. If you have an integer, that's 32 bits. If you have a byte, that's 32 bits. If you have a real, that's 32 bits. So it's always 32 bits. Well, in Siemens, if you have a digital I/O, it takes up 1 bit. If you have a Boolean, it takes up 1 bit. If you have a byte, it takes up 8 bits. And so the memory structure is a lot more optimized for these things. So depending on the type of program and the type of functions that you are using, you'll see that sometimes you could see an Allen Bradley program, if you convert the same functions and the same functionality into a Siemens, you'll see that program shrink by a factor of 10 sometimes, just because you're going from, if you have a lot of digital I/O and like ons and offs and like relay logic type stuff, that's mostly Booleans. And in Allen Bradley, all of that it's 32 times the memory that you have. If you're using mostly Booleans, you're going to use 32 times it. So anyway, I see that over on my phone I have an ad. I'm assuming everybody's going to skip the ads, but that's one thing that I haven't quite figured out on these live streams with an ad. With the ads is how it really works in the streams for you. So if you come across an ad and you miss something, just say, hey, I missed what you were talking about, because yeah, like I said before, that one trip for me and my wife to every month to a Chipotle that the ads pay for, it's really worth it. But let's talk about what motion control functions are available on this new G2 S7 1200. And it kind of blows my mind away. And again, this was the Hanover Fair kind of release. And so this was, they kind of did this as well with the S7 1200F. So like the safety processor, they announced everything, and then some of the other business groups kind of came back and were like, oh, hey, we don't really like this. Can you restrict this functionality? But at Hanover Fair, they are saying that not only can you do the speed and positioning axis that we're used to on the S7 1200 right now, but you also could do all of these other functions, the synchronous axes, so meaning gearing, and there's no restriction, so it's not just the relative gearing, it's absolute gearing. You could do the external encoder, cam tracks, output cams, measuring inputs, all of that. But then you have the actual camming and then kinematics, which is kind of blows my mind to think about the fact that they would put that here, because camming not only requires absolute gearing, but it requires a secondary process in order to interpolate where you are on the cam. So it's almost like an extra axis of where you are on your cam, and then you're putting an offset. It's very interesting. And then kinematics, at a minimum, is 3 axis. And I saw some other material on this, and I don't know if it's in this, but I'm pretty sure that the kinematics that are available are restricted to the 3 axes kinematics. So like Cartesian, like 3D Cartesian plane pickers, kind of your gantry style 3D pickers where you have 2 motors that and then one that can like move it around, and then your delta pickers. If that is the case, like y'all, people that are familiar with this channel know that before I got completely smashed this summer with work, we were designing a delta picker to be able to have here to play around with these kinematics. If that is the case, then guess what it's going to be running on it? It's going to be this G2. So we'll definitely have that, because I have my V90 drives up there. I just have to finish the actual physical kinematics for it. And maybe get 3-phase power in here, which if you were on the stream yesterday, you know how I'm going to be doing that. But yeah, so here's some of the other things like that is available for the near field communication. So like you can get these settings. So you can get like device type, the function, the hardware serial number. You can get these diagnostic data just by coming up to this thing, power it on. So is the CPU powered? Yes. Is it configured? No. Then you could get all of this data. And is the CPU configured? Yes. Then it is NFC enabled, blah, blah, blah. So you can see all the data and stuff that you could get from this near field communication, which is kind of cool. So kind of talks about here like how to migrate between the 12 and the previous series 1200 to the new G2. If you notice, the bit performance is more than double. So these are twice as fast. And the original 1200 1200 CPUs were faster than most of the kind of mid-range 300 CPUs. So I think it was this 1211C had faster processing than a 315 processor. So that bit level performance was actually better than a 315 PLC. Which if you're still running a 315 or like a VIPA or whatever, then that's kind of the performance that you're kind of giving up. Obviously, I understand if you have a process that's running on a 315. I've got a lot of customers that are running on 315 and 317s. And why would you migrate to something like this? Most of the time, you're going to be going into a 1500 and getting a lot more performance. But all that to say is, if you're looking at the performance levels of this 1212C CPU is on the level of the performance of a 1500 processor. So let me pull up the standard CPU 1500 over here and see what the bit operation is. 25, so it's 25 microseconds. So not micro, it's 25 nanoseconds. So bit level operation. So that's kind of, you're looking at getting down to almost a 1500 level CPU on this, which is pretty crazy. I mean, yeah, the 1511 is still twice as fast as the new G2, but it's still that lowest level 1500 is going to be, yeah. So this is for the 1212. Same thing on the 1214. Your bit performance is essentially cutting in half. The biggest difference between these is the actual program memory and the expandability of the I/O. So you're not really getting much of a difference in performance. It is simply you're getting more program memory, and essentially your new G2 covers any project that you can do in a 1200. So the 1214 covers all of the size of even the most expansive, the 1217. So yeah, so it's just very interesting. So this is telling you here, like if you have a 1211, a 1212, a 12 or a 1212F, here's what you need to go to is the 1212. And then anything else is covered by the new 1214, even the 1217. So don't expect to see a G2, 12, 15, and 17. I would assume that's what they're doing. They're consolidating the portfolio because the actual technology is so much better. So let's take and look. I don't think, yeah. This is kind of just talking about its integration into V20, and if you're familiar with TIA Portal, then you kind of understand what you're getting there. Portal is very efficient, and here's kind of the timeline, and I think that this is, yeah. So this is the timeline. Again, this was at Hanover Fair back in April. So, and if you have ever worked with Siemens, you know that Siemens timelines are going to change. And so what we have here, we're sitting here around the end of 2024. And initial product release, they're saying is the end of 2024. And by the way, their roadmap and their fiscal years, this would have been October, is their 2025 fiscal year. And so this calendar year marks to a like Q1 for Siemens. So you're looking at, yeah, and that's represented here. So Hanover Fair is actually in a Q3 for them. No, That's at the end of Q2. Yeah. So that's why it's kind of shorter on this. So there might be a little bit lagging behind this, but you could see that the fail-safe G2s are expected to coming. They'll probably end up in the spring of 2025, even though this is showing in like Q1. And then the portfolio elements that they don't have, like the RTD modules for temperature probes and things like that, they're going to be coming out. They're going to be working on those first. Then later on, after they get a complete hardware kind of portfolio, they're going to be going through and adding in things like OPC UA, and so actually that FIO functionality, that kind of answers my question. I can almost guarantee you that I don't think they'll do that, but I'm wrong every day. I might be wrong about that. I highly doubt that they're going to do, and maybe this thing doesn't mean what I think it's going to mean. It may not mean the remote IO, like the ET200 safety IO, because that's kind of its. You would really start to scavenge, and you would really start to take the your profit margin from from the 1500. So you have a 15. I know you have a 1511F because I have one in a project, but that 1511F is around $1,000. Like it's not expensive, and the 1200F processor is around $600. And so moving up to that 1500 to get that expanded remote IO capability, it's worth it. And so I don't like, I would doubt that they would put that in there, but like I said, I'm wrong every day. But that is the G2. And while I speak with a Southern American redneck accent and not a German English accent, so that's why I don't have one in my hand to show you, but I think this product is going to be really awesome. We definitely will be doing projects here with it on the stream, especially if it has that 3-axis kinematics. If it has the ability to do the Delta Picker configuration, we're definitely going to be working with that. And yeah, because I've got these V90s ready to go, and it's going to be good. So let's see. I've got some. Oh, I realized I missed where Ali Reza came in. See, I've got my chat over on my other phone over here, and it's not updating my chat over here. So I've missed some stuff. Yeah, so I answered that, Ali Reza, about the Gen 2, the kinematics. Yeah. So, yeah, I'm sorry about talking about Alan Bradley earlier. It's kind of just ruined the vibe here. I know that's why y'all want to come here. But no, Alan Bradley has its benefits, but if you're gonna do something really well. And there are a lot of really good Alan Bradley distributors in the U.S. Or integrators. There are less Siemens focused integrators, so that's why I tend to stick alpha to what we do best. But what I wanted to do, kind of move into now, is kind of talking about the different portal. Is this right? No. Yeah, this is right. So I was going to talk a little bit about the different functions. I'm going to flip this guy around though, because this is annoying. 57 pixels. We're going to flip it over this way. I'll show you why it's annoying. because when I point over this shoulder, like when I'm looking up at the camera like this, for some reason these are always inverted. So now I can actually point to things. So if I point over here, I can point up there. See, it's up there. It's so nice. Yeah, so Ali Reza, the kinematics. Let's talk a little bit about that. And I think I went into a little bit on it in the Motion 101 class, but I might have gone through and said, "Hey, we're going to have a advanced motion, like a Motion 102 class," because I definitely want to talk in depth about the kinematics. So let me make sure I've got this pulled up right. Yeah, I do. Okay. So on this, I have, this is from our Motion 101 class. If you notice the name of this, Motion 101 Live. So in that live stream, which is linked down below, it actually goes through and sets up this project. Now, if you just so happen to be a programmer level member, probably already have access to this. One of the things that I didn't talk about earlier, but we do have memberships, and one of the things that I wanted to add a little bit of value to, just to be able to give those memberships to you, is to give you these programs, give you these kind of TIA Portal archives that you can work with and you can kind of work along with, and then have a place to start, and then you can go. In this project, we have, I want to say it's a 1515 TF. So this is our standard, an S120, and then we've got like a little V90 hanging out here, and then some remote IO. I have not apparently renamed everything, as you always should, but in this system, we had I think we kind of had an imaginary bottling line, and we were needing to cam and gear and like all these different things. And so that's what we set up here. And for this type of application, we're using we are using a couple of different T grade, kind of like the functions that are required, a T processor is required for. Two of those is absolute gearing and then camming. And we didn't do the cam profiles in this, or maybe we did do the cam profiles. I can't remember, but there, essentially what you have is a conveyor belt that's running along, and then you have a synchronizing axis that syncs up to that where your bottle is, and then you have a filler that goes up and down based on where it is in the process. So that was what this is. And again, if you remember, then you would have I'm going to make sure that you have access to this file if you want to dig through it. But what we're going to do is I'm going to go through and show you some of the other objects in here, because Ali Reza was talking about the kinematics objects, and let's go through and add in a new kinematics object. One of the things, and I feel like I've done this in another one, but we've had so many different things, and I can't really remember them. But let's do a delta picker kinematics. And if you're not familiar with what a delta picker is, it takes 3 motors all in the same plane, and all they do is just turn. They're 120 degrees offset from each other, and you have 3 arms that have 2 segments. So you have a short segment and then a long segment that comes down, and depending on the orientation of that motor, the head down at the very bottom can move around in 3D space, and that's called a delta picker. Well, when you make this technology object kinematics, it'll chew on it here for a little bit. One of the first things that you do is you tell it what type of physical object are you? What type of kinematics are you? And this is the first one. So this is a 2D Cartesian. So you have 2 axes, you have a vertical and then a horizontal. then we're going to go down to a Delta Picker 3D, and we're not going to do orientation because that's another axis on the head. And so as you can see here, this is what a Delta Picker looks like. And it's a 3D, this is the 3D version of it, but the head down here can be moved inside of its operating envelope just by changing the combinations of these three axes. I'm gonna have to keep jumping over. Yeah, so I'm gonna keep jumping over and checking chat because for some reason my chat over here is not working on my phone. And so what a kinematic library does is all you have to do is determine or define the lengths of each of these mechanical lengths. So you have the position, millimeters, angle. So these are the units that you're going to be doing. And if you go down here to geometry, then it's telling you what are these lengths. So you have your center axis point. So this is your kind of like the rotation center axis. And then you have all of these different things. So you have D1 is how far away is from the center axis to the center axis of your motor. Then you have L1 is the length of your arm. So if this is like, and when we do our Delta Picker, we'll have all of these like fixed. So I mean, this is a fairly small one, but let's say 60.0, and then and it's even zooming in on each one of these that I'm looking at. So flange length, okay, the distance away, let's say it's 5 millimeters, because remember, all of these dimensions, when you're going through and putting them in, the further you're off, the worse the less accurate you're going to be. Because what's crazy is, if you think about this flange length here, stop moving. Let's go back to basic parameters. So if you think about this flange length, then it is going to, you can actually rotate and move this down here just by down at this level down here, having that plate, having one side be a little bit lower than the other. And so you can actually tilt that out. And so if you have a flange length that's shorter or longer like this, then you have a bigger swing. And so you have kind of a lever arm effect there. So Delta Pickers are really crazy, and the geometry that's involved in them is kind of complex because you're literally just working between three motors, and depending on their rotation and orientation and their position, you're taking that endpoint down here and moving it in 3D space, and even changing the orientation and kind of swinging it around. And the 3D Delta Picker with orientation just has an extra motor in the center that actually rotates on the head itself. So it's pretty cool stuff. For those that are hanging around, for all the YouTube Premium people, I'm sure YouTube thanks you for YouTube Premium, but I'm keeping up with the ads over here. Hopefully everyone's back by now and you haven't missed how cool the kinematics are for a Delta Picker. But what we've got here is we go through and we just put in all of our geometry. So our angles, those are going to be 120. Now, the interconnections are the drive interconnections. So we kind of talked about this in Motion 101. If you notice, this is looking for another axis. So it is looking for a I want to say it's a, yeah, it just needs a positioning axis for this one. So anything that has the positioning axis can be used as a kinematic. Now remember, you have a technology object for the axis itself, so that positioning axis has a technology object. So you can send it things like MC move absolute, MC move relative. We'll talk about that here in a second. But then you take all of those and group them together, and then you take and put on top of that this kinematic. And so you have this like another technology object that's coordinating these three positioning axes to actually to do this. In a kinematic kind of like way of thinking, you're no longer thinking about the motors, you're thinking about the tool position. So if we kind of go down here and like see if we can get it to zoom in here. Down here at this bottom, down here, this tool center point, which is on this one, it's there at that X. That tool center point is what you're controlling, because now all you're wanting to do is say XYZ in 3D space and then orientation. So that's all you're trying to do once you move into these kinematics. If you are familiar with robots like KUKA, Fanuc, Mitsubishi, like any of these kind of robot manufacturers, ABB, then everything they talk about is the tool point. And so the first thing you do is define your tool point and set your offsets. Then you have your workspace functions and all of that. And the thing about it is, do I still have it pulled up here? Not there. Maybe it's in one of these things. I think it's here. Let's see if I sorry, I'm looking up this other thing because there's a lot of, I have this document that goes and details a lot of these technology functions. And so maybe they're under extended functions. No, it's technology. Motion control. Yeah. So you have in kinematics, specifically kinematics, you have functions like, so you have your stop motion and stuff like that, but you have zones. So define workspace zone, define kinematic zone, activate workspace zone, activate or deactivate workspace zone, define tools, change tools, and those are all taking into this kind of big kinematic calculation and taking a point in space and relating it into your motors, because all of your instructions in your kinematic instructions are essentially going to be like a circular move. So take your tool point and move in a circle. Take your tool point and move from XYZ to XYZ straight. There's things called joint moves in like a 6-axis robot, to where the robot can move however it needs to move. But then there's also linear moves, to where the point doesn't go all over the place. It follows a line. And all of that is your kinematic function. So it is crazy powerful functions. But what we have is, and so the fact that they include this in this G2 is kind of wild. And the fact that it can even do it, because at a minimum, you're going to need 2 positioning axes. So just with like a 2D kinematic, you're going to need 2 positioning axes, and then this kinematic. Hey, that's actually a pretty good way of putting it. This kinematic function running on top of it. So it's kind of crazy. And so Yeah, let's go back in here. And again, these interconnections are connected to different axes of this stuff. And we're not really wanting to go too much into that, but I do want to, just as a more conservative kind of touch base on a few more of these axes. So we talked a lot about the different functions that we have in our kind of like our basic motion control profile. And again, here's one of the things though that we did in the Motion 101 class that is really good for the members is the fact that I made this little axis setup block. And if you're not kind of familiar with how to build function blocks, go back and watch this Motion Control 101 because there's kind of a little bit of a nugget in there of how to make blocks that include a lot of blocks. Because if you're familiar with technology objects, you know that there's a couple of blocks that you have to activate and run for every axis. You have MC power, you have an MC reset, and then you're going to have an MC home. Well, guess what is in this little axis setup block that we made on stream? You have an MC power, MC reset, you even have an MC stop, so a halt, which stop was actually stops the motion. And then you have MC home. So you have 4 functions built into this one block. And these are all these MC motion control functions. And if you notice, none of these, this is what's called a portable function block. And again, we can talk about it, but in order to make a fully portable function block, all of your variables inside your function block have to have the pound or the hashtag. If you have anything that doesn't have this pound sign on it, that means that if you try to take and insert another version of this block, this axis setup block, I don't even know where it is. I think it's over here in utility. Yeah, so this axis setup block, it won't work. Like if you put it on another processor, the reason why there's not a hashtag there is because you are directly linking something else. So while I might copy this whole project and copy it onto a new PLC and be able to copy that block, but if this axis setup block would be good for an axis that is running on a bottling line, a delta picker, or even like a roofing winder. All of that would be available with this axis setup block, and you just plug in all of your settings and everything, you configure it. So that's there. MC power, MC reset, MC stop, MC home. These MC functions are your motion control functions. Power turns it on, makes it available. If you're using the S120, the fans come on and it sits there and makes a lot of noise. That's MC power. MC reset is just resetting faults in both the technology object and the drive itself. And so one thing to think about is your program is no longer actually interfacing directly to the drive itself. Like if you've been on a lot of these streams and stuff, you'll see some of my agriculture programs. I've made some blocks that actually interface directly to the drive that don't use technology objects. Well, technology objects, the object itself has all the connections to the drive, and then your program is talking to the technology object. And so this technology object, you configure it once when you set the thing up, and guess what? Your code never changes, because if you need to change to a different style drive, you change the technology object. You don't change the code. So that's the power of technology object. Problem is that your code only is talking to this technology object. Well, the technology object has faults and things in it, like following error, standstill monitoring, all built into the technology object. So if you hit a reset on the technology object, it's like, okay, woohoo, I'm done. Well, the drive may also be faulted out. And so this MC reset says, hey, reset your technology object and also pass that along to the drive and reset the drive. So that's reset. So there's two different functions for stopping. There's an MC halt and an MC stop. And I think it was actually on one of the streams that I realized that we probably would want to be using the MC stop instead of the MC halt, because there's a couple of different functions that it's weird. Like if stuff gets hung up, an MC stop actually will break out the device, whereas an MC halt just kind of like stops most things, but it's kind of more like a coast to stop, where a MC stop actually stops the motion. MC home, that is a homing function, and I think I have it as an input. If you notice here, I have a variable here called homing mode. Well, that's actually an input up here, and so homing mode. And so on the outside of this block, I have a this variable right here that is homing mode. So again, if you're a member at the programming level, you'll have access to this access setup block, because you'll have access to the whole function. And you can take and either put this into a library, you can put it into a global library, or you can just cut and paste, use a reference project. If you're not familiar with what a reference project is, just pull that here. If you don't have this, if you don't have a reference project in your TIA portal, go up to View and then click on Reference Projects. And what this does is it essentially opens two projects at the same time, except you just can't make an online connection or anything to that. You can't modify this. So you can take stuff out of this code, and you can see this is opening this program here, and you'll be able to see everything that's in that program, all of the different materials, and then you can take and drag and drop. So that's reference project. Anyway, that's available to the members. And one thing, talking about the memberships, I am going to start doing a little bit more members only content, but it's not going to be anything, or not a lot of technical stuff. I put a short video in there yesterday, just kind of explaining, hey, here's what I'm going to start trying to do. This is more kind of like, as an engineer, here's how you can grow, here's things that I've learned, a little bit more of like personal stuff, a little less formal. And so if that's interesting to you, that's available to the members. You're also still going to get to keep getting all of the programming and projects and data types and things at the different member levels. But that's just an extra thing for kind of the both membership levels, that just a little bit more relaxed. I'll probably be able to post a little bit more on there, because it's going to be a little bit more less short form content, more like kind of TikTok type stuff. And just like, hey, here's what I'm doing, here's what I'm working on, what do you think about it? So if that's something interesting, that's available for you. The lowest level is not a lot. I think it's like $2 or something like that. I think the highest level is only like $5 a month or something. But anyway, so we've got these two blocks. I had a question in the Discord about the move velocity. Actually, no, a lie. It was a comment on one of the other, on another video talking about move velocity, and move velocity versus move jog. Move velocity executes, and you have to overwrite the move. So you say, I want to run at 100 millimeters a second. You start that move, it starts running at 100 millimeters a second. The only way that you can modify that value is inside this block. There is a, so let's look at cup. Nope, it's called, look at the technology object itself. So it's cup conveyor. So we're going to look at main conveyor. Oh. I'm so stupid. I need to move, because I'm wanting to move a value into something. Say if I wanted to do like a 90% of whatever the move velocity value is. If I want to change the speed in the middle of a move without firing another move, without executing another overriding move, you can use this thing here. It's main conveyor axis, and I want to say it's velocity dot, nope, or maybe it's override dot override velocity. There you go. So by default, this should be 100%, because this override velocity, any move, anything happening in like anything, if it's 100%, it's running what your value is. So if you wanted to run 100 millimeters a second, then it would be running at 100 millimeters a second. Well, on this MC move velocity, the only way that you can change that, say you wanted it to slow down to 90 millimeters a second. Well, you would either have to re-execute a move that is a velocity 90 millimeters a second right there, and then fire that move, execute. Or you could just change this override velocity to 90%, and then that gets you down to that 90 millimeters per second. Remember, the override is in percent. The reason why those numbers worked out is because I'm lazy and picked numbers that were easy to work with. So 100 millimeters a second, 90% of 100 millimeters is 90 millimeters a second. So on this line, I have this move jog function. And again, I talk in depth about all of these different functions in individual videos, but most of the time that's people coming in from Google searches, and they're looking for something on that specific function. So for you guys, explain a little bit more. Move jog, the velocity, same style of set points. So this is 100 millimeters per second. Remember, this override velocity for the main conveyor, that override, no matter what function you're using, if you're using move velocity, move position, move gearing, if you slow that down, even in kinematic moves, if you slow down the kinematic override, it's going to slow down whatever speed set point you're in. So be careful about using the velocity override. Because sometimes you'll get a number in there that you don't realize is in there, and all of a sudden everything's moving slowly, and you can't figure it out why everything's moving so slowly. And it's just because you fat-fingered, you meant to put something in one place, and you ended up changing that to 0.2, and now it's only running or 20, and now it's only running 20% of your full speed. So anyway, the move jog function, very similar to the move velocity, because it uses the same kind of values for the velocity. You have velocity, you have acceleration, you have jerk, all the same, pretty much same things. But if you change this velocity, it automatically changes and ramps up, ramps down, goes, and it's good. And so one thing, I normally end up using the move jog function in a lot of my motion control. Like our winder actually uses the move jog function. It doesn't use the move velocity, just because I'm usually adjusting that on the fly. So if I have like a pull roll that's trying to balance a load, then that pull roll needs to just move up and down. And so I can take the actual speed from here and then just toss it into the velocity here, And because I've normalized everything to degrees per second, like I have that all normalized, or millimeters per second, whatever, then that velocity is going to match and it's going to follow up and down. Now, those are those two blocks because that's on the cup conveyor control. And let's just go through some of these technology functions. So we're doing motion control, and these are V6 motion. And if you notice, we go into motion control, there's quite a few objects here. And so we'll just go through some of the basics. We've talked about move absolute, or we've talked about NC power, home, reset, all of this stuff. Talked about velocity, jog. So move absolute, again, I go into really in depth on this with in that Motion 101 class about what's the difference between move absolute and move relative. Just know that a move relative, that relative move, if you say move 100 millimeters, it will, wherever you're at, move 100 millimeters, and it'll go 100 millimeters. If you just keep going, firing, it'll keep moving along at 100 millimeters. If on a move absolute, and you say move 100 millimeters, if you're sitting at 0, if you had just done a home, it'll move 100 millimeters and move out to 100 millimeters and stop. And you're like, cool, do it again. And then it goes, cool, I'm done. Because it's sitting at 100 millimeters. Now, here's the crazy thing about it. If you home here, you do 3 or 4 relative moves, and you end up over here, and you say absolute move 100, it's going to move backwards to 100. It's always going to come back to 100. That's the difference between absolute and relative. Relative, wherever you're at, it moves the distance. Talked about those. So move superimposed. Superimposed move is taking and adding the variables, or I guess so if you do like a superimposed move, you're in the process of a move, and then you're adding the variables on top of it. So if you're in the process of a velocity move, and you say, hey, I want a superimposed move of 100 millimeters a second. You're already moving at 100 millimeters a second. Well, it's going to superimpose on top of that 100 millimeters. So it's kind of like a shifting thing. You can do it with, you can also do it with the positioning functions as well, and all of that too. So I think I have an ad break for all you. Again, have a nice little conversation with my YouTube Premium people. By the way, I have YouTube Premium on my personal account, but this account, I don't. So it's like, all right, looks like y'all are back. But yeah, where did the music go? Music. Really? Is that really all of the music? I doubt it. Let's get this. I don't even know if y'all can hear the music. When this is playing, if y'all are in here and y'all can actually hear the music, let me know. Because it's like minus 45 dB on here. I don't think it... Anyway, I can hear it. And it keeps me moving. But yeah, so we're talking about the superimposed move. I think everybody's back. We've talked about like stop. So here's when it comes into synchronous motion. We talked about that before. That this synchronous motion requires a synchronous technology object. So that's this little gear right here. That's a synchronous technology object. And let's see. There's a lot of different things. So gear in means wherever you are, if you have 2 axes that are spinning, and this one's spinning, it says, okay, act like a gear and sync up position wise, and then at that point you're going. And so you're doing this, it ramps up, and then all of a sudden you're together. Well, that's just a regular gear in. Gear in position means that you are specifically wanting to take this position and link it up with another specific position. So if this is spinning like this, and this is up here, it'll actually maybe even go backwards and go and then start spinning like that, like however it is. So it's actually linked to an absolute position. So one thing about gear in, the axis does not need to be homed, whereas gear in position does need to be homed. So phasing relative means if you are geared in and you want to take two axes and you want to phase one of them out of phase. And so like if these axes are moving together and you want to phase it by, in this case, we could say linear. So they're linked in relative gearing. So just a regular gear. And they've linked in this far. And you say, I want to phase 50 millimeters. And so while it's going, this will phase up 50 millimeters. And so it changes the actual phase. So phasing absolute, if you say, hey, I want this to be a positive 50 millimeters and it's moving along, it'll go whoop, and it'll go and phase and get into this positive range. So that's what phasing is. Offset, well, so I guess phasing would be a degree version of it. So because you have an offset, and I may have just said that the wrong way. Again, I'm wrong every day. This might be another thing, because an offset's they're basically the same thing. Shift the following value on the following axis. Shift of leading value. Oh. Shift of leading value on the following axis. Those are practically the same thing, but there is some nuance difference there, because this is changing the position that it is linked to. So, and then, yeah. A shift to the following. I wonder what the nuance is between phasing and offset, because it seems like it'd be practically the same thing, but it looks like the leading axis on this one might be speeding up. A relative shift of leading value on the following axis. So it's just saying that it's moving forward. Interesting. Those seem like the same. Anyway, if y'all know the difference between the two, yeah, just put a comment, because that's interesting. But yeah, and then, so this is all synchronized stuff. Now, you also have these things like camming. Camming is synchronizing with a relative position. So we talked again in the motion control, the Motion 101 class, that this is based on. That's there. So let's look for a little bit at some of these kinematic functions. So we have motion in kinematics. So move linear absolute, move circular absolute, move direct. Okay, so these are kind of the basics of kind of moving that point. My goodness, YouTube is hammering these ads. All right, I may have to change I may have to figure out how to put midstream rolls, because that's annoying. Ads are freaking annoying. Anyway, I'll figure that out in future streams. Sorry about that. I basically want as few ads as possible, but in order to make YouTube want to put this content out there. That's the best way to make YouTube get this stuff out here, is through liking, commenting, subscribing. But then if they're getting paid, then they'll want to put the content out there. So it's a frustrating part of the world we live in. But yeah, so we kind of talked about, I guess I can kind of talk about this. Let me swap over to my, let me swap over to this. That's that. I want MS Paint. Did I lose my paint? Looks like I lost my paint. All right, hold up. Let me add window capture, this, blah, paint, okay, that. Ooh, that's horrible. That doesn't work, does it? Hold on. Let me fix this. Once again, I accidentally deleted the thing. So, properties. That. I want this. I want paint. Okay. And now I want to see that. There we go. All right. So now when I draw on this, because again, we talked a little bit about the kinematics before, but say you have kind of this 3D space, and kind of the way we think about it is, and it's kind of hard to get this, but you have, say this is X, Y, Z. So if you have like a in space, and then it kind of goes up here, so this point would be wherever that is, and you could see that it's goes up X, Y, Z. Well, if you want to go to some other point, and we're still in kind of the same plane, we'll call it, and we'll call this X1, Y1, Z1, and we want to move to this new point here, which is X2, Y2, Z2, like this, okay? There's a couple of ways of going about it. Well, the first way is we can say, all right, I just want to go. I hope y'all aren't. Well, I know there's gonna be someone that's colorblind, and so here's red-green colorblind. So if I want to go, I can go straight to that point, right? And you're like, okay, yeah, just go to that point. Well, there's a couple of different ways that you could do that in the world of kinematics, because what I've drawn here is actually a linear path. So it's saying don't change anything about your tool and go straight from that point through all the other points. And in reference to that tool point, if it's sitting like this at point X1, Y1, Z1, I want you to move up to X2, Y2, Z2, and it just moves like this. Well, the actual motion of the axes of the actual motors, in order to make that straight path, might be really weird. You could see things going like all over the place, like it's not just a simple motion, because kinematics are taking multiple motors and coordinating them in order to actually make that straight linear path. Because if you think about it, if this is on like a flat plane at the bottom of our delta picker, yeah, it's keeping that orientation, right? Well, what if it's already kind of tilted off and oriented like that? Well, that's a big difference of the arms up at the top of our delta picker. Well, as this kind of starts to move up, I mean, it's going to have to be shifting relatively to all of the other axes. It's going to have to be shifting that plate. So in order to keep that linear motion, then and that fixed orientation, it actually takes a good bit of work. And so that's what we see like in our different values. So whoops, I didn't mean to do that. I meant to click here so that I can see the different ones. So we have like a move linear absolute, which is position kinematics with linear path motion. And I know you can't see the TIA portal at this point, but I'm just kind of, then there's move circular. And so a circular motion would be something like this. It'd be, you would parameterize moving along a circular path to get there. And if you have orientation, you actually could end up possibly having an additional XYZ. You have an orientation parameter. So this is the local, the actual point, spatial point, but then the point is the same, but this kinematic is completely different than this kinematic, even though the point is actually the same. And so like you can do all of this different stuff. And if you notice how my actual physical arm is having to move in order to get all of this, like same physical point sitting on the same thing, but very different interpretations of it. So there's, in addition to this XYZ, all I'm saying is there might be like an orientation 1, orientation 2, orientation 3, in order to actually figure out where your different orientations are. Are you from the bottom, angles, things like that. So you have all these angles. But in the world of kind of kinematics and robotics and things, you have this area here is considered your kinematic area. I guess on this, and I'll be honest, most of my experience with this type of motion is actually comes from ABB robots. Done a lot of the work with ABB robots, and they kind of use these same concepts, but all of it's here in this kinematic stuff. Joint space in order to identify. Yep. So, So, Joseph, that's exactly right. So kinematics is mapping all of the joints and their functions to be able to actually put it into a coordinate space. And you have these different functions that are available to you. So a direct absolute. Now, so there's a direct function. So I would actually have to look at the different paths between like the linear and direct, but there's normally what you would do, you can really see this on a 6-axis robot. On a delta picker, it might not make too big of a difference, but because you have these orientations, then there's, how do you get to that orientation? A linear move is going to be, you're probably keeping the same orientation, or you have some sort of linear orientation difference. And if you notice, like, again, it's really easy to see on a 6-axis robot, aka my hand, because you have an elbow, an arm, 1, 2, 3, 4. So you could see, and then 5, whatever it is. So you can see all the different axes of motion. And so in order to have this kind of like point, I'll pull it back a little bit. You just won't be able to hear me very well. That orientation really matters a lot. And so if I change orientations, my kinematics really matter if I'm moving from point A to point B in a linear. Now there's another way of like saying, okay, I have all 6 joints and I just want to do a joint move to a position and orientation. So instead of having to like follow this weird path and mess up my shoulder and like do all of these things, just say, I want this orientation at this point, and then I want to move to this orientation at this point. And I don't have to worry about keeping it on a line. And so what it may do is just go like that. And so the actual point in between the 2 points could be wherever, because it's called a joint move. And so you're just taking the actual axes and saying, okay, my first position is here. Here's what all the axes are. Here's what all the joint positions, all the motor positions are. And then what are the ending joint positions based on my kinematics? Okay, just go to that. And what happens is you'll see this kind of like flop where, especially in a 6-axis robot, it'll just kind of flop around and just and then end up at the point. It looks really weird because you'll be sitting in some orientation and it'll like whoop, and it's there. It's at the new orientation, but the actual point goes all over the place. So that's what the difference between these functions are. And so kind of a joint style move, the actual end point could look like like that. And that's just because it's doing the most efficient motion on each joint. And if you're not coordinating the end point position linearly or some sort of path, then it's not tracking the path, and so your tool can go anywhere. Joint moves are very dangerous, by the way, if you're doing robots. And I would have to go through and look and see which one of these actually are that, but they are there. Kind of go back into these other things. I'll flip back over real quick to a portal, because, and I'm going to move my head over to the other side because we're going to be talking about stuff down here, because we're talking about zones. So again, zones, workspace zones are, you can do things, if you were working in a workspace, you'll have a workspace center point. So a workspace coordinate system. So if I have like, I don't have a box or something. It's really easy if I had a box, but we'll talk about this. So relative to my desk, 0, 0 is down here on my desk. I'm tapping my desk. If I put my workspace like this, if I put my workspace somewhere not on the desk, there's an offset, an XYZ offset, right? And what I can then do is say, okay, I'm working on this book. This is 0, 0. This is 0, 0, 0. This is positive Z coming towards the camera, negative Z going away from the camera. So I might have X, Y, Z like this, and it's off at some weird angle. But all of my coordinates are still on this plane and Z. And so if I'm designing my part, it's all X, Y, Z, simple math. And so all the numbers and everything are based off that. When you actually go to put the part into real space, your fixture might be weird. It might be sitting like this. And so there's these zones and coordinate system functions that are in in these different in these different functions. And again, I'm not completely familiar with them. I know in like my work in ABB gets to translate over into this because it's just kind of like different programming languages, different functions for different things. But you'll have some way to define this coordinate offset. And so you have a nice little part that you're wanting to weld on this space. Well, if it's sitting flat on my desk, then my original coordinates and everything, my tool path is what it's called, tool path, would work on that space. You can create an offset, and then all of a sudden, my robot, I can use the same program, I can use the same tool path, but now it's sitting at some weird angle, and the joints, the motors perform absolutely different than if it was down here on my desk. So that's what these zones and kind of frames and transformations, that's what all of these different things are. Because the cool thing about it is, imagine, for example, that you have parts coming down a conveyor, and each one of those parts could be one of 3 different parts, but you're wanting to laser cut or weld in your logo onto those 3 different parts. One of them's oriented like this, one of them's oriented like this, one of them's oriented like this. If you did that, you would hate yourself, but production is run by management, not engineers, right? So what you could do is just set up 3 different objects, and then you could attach those objects to a moving coordinate system. And if we were having to do this in our brains and like actually have to track this, it would be horrible. But these type functions give you the ability to complain to your managers about the impossible tasks that you have given them, and then run 3 different functions, and it takes like less than a day of work to do. But you don't have to tell them that because all you do is just set up your 3 different coordinate systems for your 3 different parts. And then there is a track conveyor belt function that puts those coordinate systems on a conveyor belt. And it's all like built in. So again, the kinematic functions in this are insane. Yeah, I'm telling you, kinematics like are very difficult to be able to like actually work through what's going on. And so once I get my Delta picker, and over the winter, I'm definitely going to be able to have more time to figure out Delta picker stuff. Once we get all of that stuff going, we'll be having fun and doing some cool stuff with these different functions. But yeah, so how long have we been going so far? We're coming up on 2 hours. But yeah, this kinematic functions with these G2, I just don't know. I don't know what the capabilities will be able to be, because it just seems, again, a lot of this stuff goes back to not necessarily being about the technology. A lot of times it is about the product marketing and being able to support customers and different business groups and a lot of this different stuff. And I can't really blame them, because I mean, you have a company that is supposed to be making money, and a lot of times I remember, and this is kind of getting off into just a little bit of personal experience, but they came out first with the G120, the G120 modular system, and then you have the G120 compact. Well, they were having trouble getting into this wastewater pump fan kind of market, especially in the US, because you had companies that had really, and I'm going to use the word cheap, they might have been good, but they were inexpensive drives because they were it wasn't really apples to apples. I always tell people, like, we do work in both in heavy industry, light industry, and then agriculture. And so I've designed really heavy duty stuff for steel mills and coal mines, and that's where Siemens and ABB drives really excel in those heavy industry. You see them a lot, and it's because of the way they're kind of designed from that ground level up. Yeah. So, the like, the fact that when you go to try and put those types of systems into systems that don't really require as much of a kind of feedback, or not feedback, they don't require that amount of robustness, then you end up getting into these things to where you get priced out and you can't enter into those markets because, yeah, your drive is a lot better than the competition's, but you don't need that good of a drive for a fan that's in a well-cooled environment that like has very stable air density. So what Siemens ended up doing was like, all right, we want to enter into this wastewater pump fan drive space. And so they came out with the G120X, and the G120X, they had this like G120P that was not good in the US, and it just because of the voltage on it. The decisions that they made for the G120P made it to where they could not use that drive in the US. So by the way, if you're watching this in the US and you have a PM230, I believe, you really need to migrate it. It's a ticking time bomb. But that PM230 just was not good worldwide. So they came out with this G120X, and it was a less expensive drive. And the way that they did it was they're like, hey, this is only supposed to go on pumps and fans. And here's how pumps and fans works. They never run over their rated speed for the most part. If you have some sort of like over voltage, or not over voltage, but if you have some sort of like overload situation, it's going to be very minute for a very short amount of time, usually. Otherwise, you're going to have to shut down anyway. And so they kind of brought down the robustness of the heat, the thermal capacity of these drives, and they work great. They work wonderfully for the right applications. Well, all of a sudden, you have these people that are like, oh, hey, and especially in the U.S., I don't know how it was worldwide, but in the U.S., you had people going in and be like, oh, hey, this is a cheaper G120. I'm just gonna put that on whatever now. And it started taking away applications of like for like. So if you have a 100 horsepower drive and you're like, yeah, I technically don't need the overload capacity. Like, it's in a good situation. So I'm going to go, yeah, it's not a pumper fan. It's a conveyor, but it's a really low duty cycle conveyor. So I have this cheaper option now, or this less expensive option. And you started robbing market share from yourself by releasing this product for something else, and then people not really using it for the right thing. And I almost see this happening with this G2 technology, of there being some sort of restriction not based on the technology, because the technology, I mean, gosh, like processing technology is crazy, and they've probably already throttled back the technology in this G2 processor anyway. But I don't see, I think that they would be limited to like a Delta picker and so many IO points, like some way, because if you start taking away, getting to where people are like, oh, well, I want to run 3 delta pickers off of this, but I want to run them at super slow cycle times. They're not really high speed stuff. I think there's going to be some sort of limitation on it. And so I would not be surprised if you see like some sort of restriction on some of these kinematic functions to where you don't have some of the more advanced functions like the conveyor belt tracking, and or you don't have like workplace transformations, something like that. You'd be like, well, why wouldn't they do that? Every decent application requires workpiece transformations, and it's like they come in and be like, well, we wanted to give you an option, but we do have this other option, this 1513T, that has that. And so it's like, yeah, I'd be interested into see all of this. But yeah, I see there might be some people that are a little behind on the stream commenting. So Mohammed, when you get to this point, I hope all of the kinematic technology object discussion has filled in well for you. But yeah, I had intention of maybe going through and talking a little bit about something that came up in the Discord. We've got a few people on here right now that might as well talk about this, because one of the things that we have now with these technology objects is we have kind of all of these different ways to economically perform different motion functions. And so I'm going to try to bring this up, and I'll clear this out. Let me do this real quick. Clear that. Because we had, in the Discord, we kind of had a design discussion about the best way to do a crane in today's technology world. And cranes are interesting. They have a lot of different things that are very industry specific. And I had the opportunity a few years ago, as a distributor, to go through some really cool classes and work with some really cool companies on some crane applications using Siemens drives. And I learned about a lot of the intricacies of the designs of these things. One of the first things that kind of the VP, or I think he was a VP at the time, or president maybe, of this company, he was saying, like, cranes are not, like, you have to size them appropriately. Like, there's so many different things, and he was kind of skeptical whether or not Siemens drives would be able to do it. And well, I went through and like looked up all of these crane function sizing and like all this stuff, and just, I'm like, yeah, here's how it is. Here's these overload, and look up some of the crane regulations about hoisting capacities and torque ratings and like all this stuff. And I'm like, yeah, we're good. And he was like, I don't think you understand it. And I realized that as I actually started working with the crane group at Siemens, which, by the way, if any of the Simacrane guys, I don't know who all is there now, but you got Roland and Tomas and Manfred and all the guys. They taught me so much, and I'll be honest with you, Thomas Fapa and Manfred, what was his last name? I can't remember Manfred's last name, but they taught one of the most difficult classes I have ever taken by Siemens. It was a stinking physics class, and it was crane sizing. It was like, all right, here's how to like size these crane motors. And going into that class, it was a certification class. We had homework. And for you, like, US people that are watching this, they're like, wait, you went to a training class that had homework? And I'm like, yes, it was taught by Germans. And we had physics homework of like doing free body diagrams and like all of this craziness. And at the end, I think we had like maybe 15 people in the class, and I think like 3 of us passed. It was rough. And but yeah, it's because there's so much to do with cranes and sizing. They deal with so many different things. And in our Discord, we were kind of looking at what's called you have like a what's it called? I'm gonna forget all my terminology now, but it's like a 4-point crane. So you had two cross axes, so 2 rails, and then you have 2 axes that are done like this, and then these are actually bound together. So you have your 4 rollers have a space in between them. So I'll draw it like this, just so it kind of is a little bit easier to see. But you have a wheel here, a wheel here, a wheel here, and a wheel here. And one of the things that we kind of like kind of think about, you're like, okay, well, I'm having to coordinate 4 motors. How do we want to do this? And I had a long time ago, I'm like, oh, you want to load share between all of these motors, right? You want to actually, this is, we've got a load sharing class, like on one of our live streams. Like, this is the same thing. So originally I looked at this, it's kind of that. And I worked with a different company that had one of these applications similar to this. And that was kind of where they were trying to do, is they were trying to load share between these axes. Because there's really three ways to go about it. You can go in essentially one drive, and in volts per hertz. And what this happens though is, as you start moving the trolley back and forth, you'll put more weight on one side over the other. So if you move to this side, then you're going to put more weight on these and less weight on these. So you're going to inherently kind of tilt. You won't actually tilt, but you're putting more load. The thing about most of these rails, or I mean, I gave it away, but most of these cranes ride on metal rails. And most of these kind of industry cranes have metal wheels, like railroad wheels, that, if you're familiar with them, it kind of are like this. And you have your rail sitting like this right here, or however, and you have metal on metal. And so there's only so much friction here to go around. And so as you start to shift and unload, then you're always going to be kind of putting more load on these downstream motors. Well, there's a problem with that. If you're only running one drive, then these motors down here are going to take all the load, and these motors up here are basically not going to be to having any load. And so all of the pressure is going to be on these wheels down here. You're like, okay, that's fine. Cranes move back and forth all the time. Well, in like a steel yard, or like a roll shop at a steel mill, usually you will have kind of the layout of your building is you'll have your kind of all your rolls will be over here. And so your crane will end up going up there, getting it, coming back, and then moving down the length of your shop. And so most of the time, your rails are on this side are going to be getting more load. So you're like, well, Jason, how in the world can I do anything about that? And the thing about it is there's really not a lot that you can do about that loading. But what you can do is if you can design your crane so that when you are in this process, you're actually you actually design it with the intent of, hey, I know that it's going to do this. I know I'm going to have these problems. So, sorry, I'm getting music back going. You might be able to do something. So in this case, OneDrive probably isn't the best way to do this, because if this starts kind of loading, yeah, you're going to get the side-to-side loading. But if you kind of get your load back here, then you'll start crabbing. And this will take all of the load. These will have none. And your rails, your wheels will start moving up against this, and you'll start rubbing this this flange here in between this face and this face. And you'll actually start rubbing off this flange eventually until it can fail. And you don't want to have that type of failure. So one of the things that you really want to do is try to keep these rails from touching, these flanges from touching. Well, so one thing you can do is say, okay, I'm going to try and prevent this by putting 4 drives and do speed control. And that's a good way of doing it. The Simicrane technology has all sorts of crazy stuff that's going on with it. But most of the time, they have 4 drives running 4 different set points. And you say, okay, well, what's the best way to coordinate this? And you might go in and say, okay, well, we could set up a master slave torque follower, like we've done on like our load sharing or our other videos. The problem with this is if we do this, all of these motors, all the slave motors have to try and run faster than the master. They're always having to try to run faster than the master. So, and then it's trying to share the load of that. Well, because of this shift, the master, if you shift towards the master, all of a sudden the torque available in all of your slave motors will start to shoot up. And they're already trying to run faster than the master. And so what you'll do is you'll have a situation to where the master's torque will start to go up, and these over here on this off side, they'll slip and they'll hit up. And if they never get traction, then you will just sit there and spin. And what this will do, it'll wear out it'll wear out this part because of slippage. You're gonna wear down anyway. It's wild, especially in like coil cranes and things. You're gonna wear down this flange anyway. But with slippage, you're gonna polish that rail, and then all of a sudden you're basically not going to ever get any load sharing on that. So in a industry crane like this with rails, you never want to slip. And so load sharing in that way is not a good way to do it. Well, the only other way to do it would be to have a positionally controlled setup, and you're still going to get imbalance in the rails. But what happens is if you take and you have a position master, and then these aren't torque slaves, they are sync axis, then the position, aka speed at any given time, or speed over time, are going to be linked together. And so that reduces any slip that is in on the rails. It should almost not slip at all, because what happens as this master side, as you move this over onto this side of the rail, this master's torque will start to go up, but these rolls at the top won't slip. And so you're not going to have any of this walking to where the rails go back and forth like this. And so a really easy way, if you have this four motor setup or like a wide gantry style overhead crane, then you're, the best way to do it is with a positional master. Overall, long term, that is going to be the best way to do it. Thing about it though is you see many cranes out there that are doing this one drive volts per hertz setup, and they just load balance and it's fine. One thing about this new G2 is because of the synchronous option, the price point to put this technology starts to come down. You're saving a couple $1,000s. All right, now you're using technology objects. You're not having to use expensive drives. You can use inexpensive drives. So you can bring this higher end technology that makes these wheels last a lot longer and less maintenance. And you can bring it in with this G2. And so these are the type of applications that I'm really excited about with this new 1200 G2 processor, because we were restricted before to the to just a couple of motion resources. And the thing about it, to be able to do a kinematic, I feel like you would have to be able to do what we just saw, like a real master, and then 4 or 3 individual slave drives with, or synchronous drives with a with that positionally connected synchronism. So I think those are going to be the opportunities that you're going to be seeing out there, more than the kinematics and the craziness, because I really think that they are going to limit the functionality in the kinematic realm for this G2. There's just so much there. If you've worked with kinematics, or you worked with this technology, you know that it's difficult. But I will say, and this has been a pretty good, chill, relaxed stream. I love the international crowd. I try to do these earlier to get y'all going, to get y'all involved. I appreciate everything. I appreciate everything that this channel kind of works together on. And as we kind of get these new technologies in, I look forward to bringing them in to the shop, testing out different things. I like testing new technologies, just to see what we can put into our equipment. We do build OEM equipment. We do more than just integration. And so in our OEM style work, we have the option to come in and be like, okay, do we want to put something here? Do we want to make this change? What's the best way to do this process? And fortunately, our most of our customers that we end up working with, we work with them because they can hear the value of kind of forward thinking and technology and things that aren't just buzzwords and aren't just kind of keeping up with trends, but actual real practical uses. And I personally, especially when I worked in distribution, um, I got accused of only being kind of attracted to the fancy problems and the new technology, and I do that. I love playing with new stuff, but there's some like tried and true technology that is still out there that's like, all right, this is probably a really good way of doing it, and you can reinvent the wheel and it still rolls down the street. and like, yeah, you might get a little advantage of it, or you might be able to integrate more technology into kind of like the data side of it. But at the motion level, at this kind of like this core level, it's like, yeah, we've been moving things in a certain way for a long time. And I hear, so I am on LinkedIn, and it's funny kind of like seeing these marketing and industry people talking about industry 5.0, and it's just a word to them. And it's like, all right, what is it? They're just trying to make some buzzword, and you don't even really understand what it means. And like that, the Industrial Revolution V10, and then you had the second revolution and the third. That third was this manufacturing technology that was like, oh, hey, we have these like physical devices that can actually really impact the lives of people around us, like robotics and like actual robots were the biggest thing there, because you had this automation. You had the Industrial Revolution, and then kind of like process revolution, and then the automation, and then now industry 4.0 is kind of the data side of it, and artificial intelligence, and kind of like learning to replace the thought process behind it. And you see all these people talking about industry 5.0, and I'm like, you don't even understand what you're talking about. But I still see this new technology, and I'm like, oh, I want to use that. I want to do that. But then at the same time, it's like, what are we gaining from it? So anyway, I know it's getting late for those of you that are in Central European or even further east. Here in the US, hopefully you are almost on vacation if you are not already. And so I'm probably going to end up the stream here. It has been a great stream, and as always, if you've made it this far and you haven't liked the stream, like it, get it out there. I know that these are longer form, that a lot of people don't kind of get bits and pieces out of it. I'm going to start trying to kind of clip stuff out and bring smaller form content about the individual topics, but I like talking about all of these things just kind of in this open form. So I really appreciate all of everyone that comes in on these streams and kind of interacts and is part of this community. I want to thank all of the subscribers. If you haven't subscribed, there's a ton of stuff here that is available to you, and subscribing and liking videos and comments honestly really helps out a lot, because it gets the reach out there. There's not too many people that are working and watching automation videos, and so the more we can actually get out there and see, maybe we can get these videos out into people that it's like, oh, hey, maybe there's a different way of thinking about something. And of course, for those that do have memberships, I'll be making sure that the project that we have today or had today is still available in the directories. And I'll also be, like I said earlier, getting a little bit more kind of less technical, more just kind of like relational videos in for the members only sections. And YouTube, yeah, Lucid, if you haven't noticed, I'm an automation nerd too. And so Yeah, for those in the members, like YouTube loves making money, and like I said, I've said before, I don't make a ton of money off of this content, and it's really not about it. It's really about getting the word out to people that need a little bit of a community, and that's why I love the Discord. Um, and the more memberships there are, even if they're at the smaller level, YouTube's making more money off of that, and so they're going to push this channel out and promote the channel more. And so it's kind of like the free YouTube advertising. The edited content does really well on YouTube, or not YouTube, but Google search. So we've got some good stuff that I've catered the metadata for. But getting it out to new YouTube viewers, memberships are great, and memberships are a great way of doing that. And I'll try to always give you the members value for what they have or for what they give. But in the meantime, if you're in the U.S., I hope you have a wonderful Thanksgiving holiday with those that you care about the most. And if you're not in the U.S., I hope you have a great rest of your week, and are able to have an easy winter, or if you're in the southern hemisphere coming into the spring, summer, go through that. In the meantime, I am glad that you were here, and I hope to see you next time. Always remember, comment if you have questions, hit up the Discord. Until then, I will see you next time.